One can also use integration to calculate volumes. For example, if we have a cone, and a cone we can create by rotating a line. If we have a straight line here, we can rotate it around the x-axis. Then we create a cone. If we take a half circle and rotate it around the x-axis, then we create a sphere or a ball. So in these cases you can actually calculate the volumes of these objects. So let's see how you can do that. So let us take a general curve here in the xy plane, f of x. And then we rotate this graph around the x-axis. Then we get a three-dimensional object. To calculate this volume here, then we can slice the figure up. So if we take slices here of the volume with the width, let's call that dx, and we make the slice at x. Then if we calculate the volume of this one, and then add all those kinds of volumes here, then we get the volume of the object. So that's the ID. So what is the volume of this slice here? Well, if this slice is small, if this is small number, then we can approximate this as a cylinder. So if we take one of these slices, and then this side here is the x, that is the height of the cylinder. And to get the volume, let's call the volume dV. Then the volume of this one is just the base area times the height. And the base area is just the area of a circle. And then what is the radius of this circle? Well, it's just the function value, because you have here, the height here is the function value. So if you take the function value as the radius, then we shall take pi f squared and then multiply with dx. So this is the volume of this slice. Now we need to add all these slices. And in mathematics you write the sum as a sigma. So we need to add all these slices. In the limit when dx becomes very small, this is just making the integral. So the total volume is the integral of this, and that's just the integral of this here. And here we have to take the limits, and that's from all slices from A to B. So here we should take all x from A to B. So we arrive at the formula for calculating the volume of an object like this, and that's just this. So let us see some examples of how this can be done. For example, let us take a volume of a cone. So if you take a straight line, y equal to kx, going through the origin, and we rotate it around the x-axis, we have created a cone. So in our case here now, f of x should equal to kx. And here k is just some constant. So let's see that we can derive the volume formula for a cone using the integration. So then we should take the integral from the origin, 0, until the height of the cone, h. Then using the formula we just had, then we should take pi square of the function and dx. And in our case, this is the square of this one. And these two just constants, we can put them in front. So then we need to take the antiderivative of x squared. Then we just put in the limits here, h and 0. And this is 0, so it just simplifies to this. And let us write it like this. So here I divided up this one into h squared and h. And why is that? Well, because this is kh squared. And what is kh? That's the radius here. Since if we put in h here into this formula, we get kh. So this side here is kh. So this is just the radius of the cylinder. So we have radius squared. So we can write this as pi thirds times the radius squared times h. But pi r squared, that's just the base area here. So we can write this a times h divided by 3. And if you now remember the formula for volume of a cone, and if you've forgotten about that, you can look here in the previous lecture. Then you see this is just the volume formula for a cone. So we have derived it using integration. And we can also calculate the volume of a ball. So now we're going to show that the volume of a ball or a sphere is just 4 pi thirds r cubed. And then we're going to use integration to show that. So we again use the formula here. So we want to take this half circle and then we rotate it around the x-axis. So you want to go here from minus r to r, the radius of the sphere. And remember now that r is just a constant in this case, if you have chosen a sphere. And here is written the function of this half circle. So where have we gotten this from? If you take a point here on the half circle, then this distance here is just the radius of the sphere. And this one here is f of x. And here we have a right triangle. And this value here is x. So for Pythagoras theorem we have that this squared, x squared, plus this squared, which is f of x, that should equal to r squared. And if we solve for this one, we get this. And if we take the square root, we get just this one. So that we can use here now. So now we have the function for this half circle. And if you take the square of this one, it's written here. And multiplying in pi. Have we chosen a half circle, this is just a constant r. So the antiderivative of this one is just the constant times x. And here is a constant times x squared, so the antiderivative is x cubed divided by 3. And if you put in the limits, we just get this one. And let's continue up here. And here we get 3 minuses. Taking these two together and these two together. And then changing this into thirds. We see that we have arrived at the volume formula for a sphere or a ball.